Okay, here's an application of Newton's second law with an angled force, so it's in 2 dimensions. We've got a person pulling their 17-kilogram suitcase along by a strap with a force of 30 newtons at an angle of 35 degrees above the horizontal. We're going to neglect friction. That's what if friction is negligible means. What is the acceleration of the suitcase and the magnitude of the normal force on the suitcase? So let's go ahead and get started this way here. We've got a force diagram that we're going to draw. There's our suitcase, and we've got a force of weight working downward. We'll figure that out in a second. We've got a normal force working upward. We've got the force of that pull working at an angle of 35 degrees above the normal. And that force of pull is equal to 30 newtons. We're told friction is negligible, so friction isn't acting on the object. So we won't have a frictional force opposing motion. And I think that's it. So we took care of our force diagram. Next step is to rotate if it's on a ramp. No ramp, so we don't have to rotate. So we skip right to breaking angled vectors into components. We've got one angled vector right here. So what we'll do is we'll break that into the x direction and the y direction. Those two forces will take the place of the angled force. So when we go into calculating and developing our equations in the x and y direction, we will ignore this 30 Newton force and work with these two forces here. So Fp in the y direction. We have enough information to go ahead and figure up the force of weight and the two components. So let's go ahead and do that. Let me get a calculator out here. The weight is going to be 17 times 9.8, which is going to be 166.6. 106. Let's do this in a better color here. 166.6 newtons. I'm going to leave it as 666 because it's kind of evil. The x and y components, let's do that off separate here. So we've got Fp in the x direction. That will be the adjacent, according to Chief Sokotoa. This is my adjacent. Here's my angle. Here's my hypotenuse. That 30 newtons is my hypotenuse. So we would use cosine. So we'd have 30 newtons times cosine 35 degrees. Calculate that in a second. So that means that Fpy is going to be the opposite. So that would be the opposite side. This is my hypotenuse, 30 newtons. So it's going to be 30 newtons times sine of 35 degrees. All right, let's go ahead and get the calculator out. I want to make sure that I'm in degrees. I am in degrees. So I can go ahead and go 30 times cosine 35 degrees. Close up that parenthesis, and we get, I wonder if anyone's going to get that. You know what? I'm going to pause here for a second. All right, it wasn't for me, so I don't have to worry about it. That'll give me 24.6 newtons. This is 24.6 newtons. And then let me do the other one. That's going to be 30 times sine 35. Close up that parenthesis, hit enter, and we get 17.2 newtons. So I've got my x and my y component for those two. I'm not going to try to fill them in on the diagram because it's going to get kind of crowded. So we're asked to find this and the acceleration of the suitcase. So we've broken into components. So the next thing we would do is evaluate the motion. This is obviously accelerating because we're asked to find the acceleration. So we're going to assume that acceleration is not equal to 0. We'll work on that assumption. And we'll go from here. So let's see here. So after evaluating motion, then we go ahead and we use some of the forces. So let's go ahead and go to our x direction, because that's going to be the direction that this is moving. It's going to be moving horizontally. It's not moving up and down. It's being pulled along. So in the x direction, we've got the sum of the forces is going to be equal to mass times acceleration, because acceleration is not equal to 0. Two ways that we can get sum of the forces. Sum of the forces literally means sum of the forces. We add them up. We can add up all the forces. Or mass times acceleration. Two different ways, and we can set these two equal to each other. So what we're going to do in the x direction is we've only got one force in the x direction, and that is Fpx. So what we've got is Fpx is going to be equal to ma. So let's go ahead and put in our numbers. We know Fp in the x direction is going to be 24.6 newtons, is going to be equal to the mass of the suitcase, which is 17.0 kilograms, times the acceleration. So we're going to divide both sides by 17 to get the acceleration. Acceleration is going to be equal to, excuse me, to 24.6 newtons divided by 17.0 kilograms. Go ahead and do the division. And we get 1.45 meters per second squared. Little sidebar here. A newton is equal to a kilogram meter per second squared. So what we've got is we've got a kilogram times a meter over second squared. That's on the top. And we've got on the bottom a kilogram. So, oops. On the bottom we've got a kilogram. The bottom of the top goes to the bottom. So that would be kilogram meter over kilogram second squared. Kilograms are going to cancel out of there, and we get meters per second squared. That's how the units work on that. Now in the y direction, because we need the normal force, in the y direction, sum of the forces is going to be equal to 0, because this suitcase is not moving in the up and down direction. So this, I guess I should specify this, this is in the x direction. In the y direction, a does equal to 0, because this thing is not moving up or down. So what we can do is we can go ahead and go sum of the forces, or adding up all the arrows in the vertical direction, which is going to be F normal plus F of weight plus Fp in the y direction. That's all going to add up to 0. So we get F normal. It's going to, F normal plus a negative 166.6. Let me write that a little clearer. Negative 166.6 newtons plus a positive 17.2 newtons is all going to add up to 0, because that's in the y direction. So that means that F normal is going to be equal to Let's do this. 166.6 minus 17.2, 149.4. 149.4 newtons. So there are my two answers. And we're done. Again, just follow the steps. Everything will work out just fine.